Hello everyone. Today I'll be working through question 2 from the practice final for Physics 457 for the upcoming final exam. Question 2 reads, the sky is blue. Part A, explain why Earth's sky is blue, not violet or green or some other color. So we'll start with part A, and part A to me is I use some different skills, some different knowledge to answer this question because I have both an astrophysics degree and a physics degree. I'm going to use a little bit of my astrophysics knowledge and a little bit of that type of information that I know in order to explain my answer to this problem. And I encourage you, when you're answering these kind of conceptual questions, to not only try to remember what you learned in Physics 457, but how you can apply your knowledge from other classes into answering a question like this as well, because that might help you in order to get a few more part marks, get some conceptual concepts down, and also it'll help you develop your own understanding and show that you know what you're talking about when you're explaining why the sky is blue. So we'll say that the sky is blue, and the reason for this is because that when light from the sun comes into our atmosphere, it gets scattered. So it's known as what's known as Rayleigh scattering. And how the scattering works is that light from the sun will get absorbed by the molecules in our atmosphere and then re-emitted. And this scattering occurs at a certain angle, and it is dependent on the wavelength of the light to the power of 4. So this is the Rayleigh scattering formula. And I know this from astrophysics. I think that's in Griffiths as well. I couldn't really find it when I was looking, but this is something that I had in my knowledge base. And I'm sure that when you learned about radiation, you learned that scattering occurs dependent on the frequency or the wavelength of that light. So what we'll see is that when light from the sun comes into our atmosphere, depending on the wavelength of that light, so the sun has a certain black body that it emits at, it's going to emit light like this, like a black body function. It's going to have a certain peak. That peak is green light, and we're going to see that when this light from the sun comes into our atmosphere, it's going to get preferentially scattered depending on its wavelength. So red light, which has a longer wavelength, gets scattered less and just passes straight through, essentially straight through the atmosphere and comes down to Earth. So we just see that red light comes and hits us. Blue light, however, on the other hand, has a shorter wavelength, which means that it will get preferentially scattered. So it will get absorbed and re-emitted by the molecules in the atmosphere, and will get scattered out. And what happens is, if we have a ray of light coming in, it hits a molecule, and it gets scattered off in this direction, we see then that light going this way. And this happens all over the place, and we essentially have a scattering or a cascade of blue light and violet light and any other light that's not preferentially red that passes through into the atmosphere. And therefore the sky appears blue. Now we would say that, again, because this function depends on 1 over the wavelength to the power of 4, the shortest wavelengths will get scattered the most. So something like violet light would get scattered even more than blue light, and so the sky should appear to be violet. But because our black body function peaks from the sun, the light emitting from the sun peaks in the green wave band, right around the wavelength of green light. What that means is that there's not actually a lot of violet light coming from the sun. There's not a lot of violet light emitted by the sun that can be then scattered in our atmosphere. So blue light is what's preferentially scattered, and that's why we see that the sky is blue. Something else that's interesting to note, and might just kind of be a quick cool piece of information for you to think about, or then maybe apply on an exam question, is that when we then have our sun like so, or our Earth like so, and we have the sun down here, so the sun is setting, and then the light is coming through the atmosphere on the horizon, so it's like a sunset. Sometimes when you look at a sunset, you see that the light appears to be kind of orange or pink or red. And what this means is that we're actually seeing the light passing through more material. So when we're looking off at the horizon, the light coming from the sun passes through more atmosphere. If you think about that, it's on the angle on the edge, it's coming through. When it's coming directly down, it has a shorter path length to go through. So the light will pass through more material, which means that the more blue light will be scattered. And therefore, only the light that passes through that we're able to see is that red light. So that's why the horizon appears red or pink when we look at a sunset. Also, this light gets preferentially scattered depending on the amount of material in the atmosphere. So, for example, when it's just passing through normal atmosphere high up in the clouds, it's going to become kind of blue and it's going to be scattered. But when it's passing through more material closer to the surface of the Earth, then it's going to pick up all of the pollution and all of the additional particles that are in that atmosphere closer to the horizon when you get closer to the city level. So that light will be even scattered even more, and you'll have even more blue light scattered away because there's more particles for that blue light to hit. So what that means is that the light traveling through the horizon, the light that we see during a sunset, is red, or it's all of the blue light has been scattered away because we see that that light is preferentially scattered depending on its wavelength. So again, this question asks why the sky is blue, and we know that because of Rayleigh scattering, or that the amount that the light is scattered when it comes into our atmosphere is dependent on the wavelength to the power of 4. So shorter wavelengths will be preferentially scattered, and then red light will just pass through and come down to Earth, and we'll see the blue scattered across the atmosphere, and that's why the sky appears to be blue. So we'll continue on with question 2b. And question 2b asks, is the light from the sky polarized? If so, draw a diagram to show which way the light from the sky is polarized and explain why it is polarized. If not, draw a diagram to explain why the light coming from the sky is not polarized. So let's start by drawing a diagram and kind of see what's going on in this question. So we have our light from our sun. The sun is emitting radiation, it's emitting light, and that light will propagate towards us as an electromagnetic wave. So it'll be like this, traveling towards us. Let's say for now that the propagation is into and out of the board, or into and out of the page, like so. So it's kind of oscillating into and out as it comes towards us. And then it's going to, so this light is unpolarized. The light coming from the sun is unpolarized. When this light is initially emitted, it comes in, that's unpolarized. As soon as it starts interacting with material, however, it will become polarized. And we can see this because, for example, this electromagnetic wave is coming in, it's oscillating into and out of the page, and it's going to run into this diatomic molecule, essentially this dipole here. And this dipole is going to, in my crude terms, is going to ride that wave. It's going to oscillate into and out of the page as if it were going up and down on a water wave. It's going to go into and out of the page and ride the electric field as that electromagnetic wave comes in. And what that does is that causes a dipole moment to point like so into and out of the page. Because we can see that this dipole will be go up and down into and out of the page on this wave. So not up and down, but into and out of the page on this wave. It's going to follow the oscillation of that wave. And then it's going to move up and down like this, into and out of the page, sorry, like this. It's hard to see on the diagram and explain it. And what's going to happen with that oscillation is it's going to then radiate, because we know that an oscillating dipole will radiate energy. And we can see that this is going to radiate energy in what's called a Griffith's donut. So we can draw the donut like so. This is the center of the donut. And we see that the dipole moment goes straight through the center of the donut. And what that means is that there will be actually no radiation emitted into or out of the page along that axis of that dipole moment. So the radiation will propagate outwards in the kind of donut fashion. So that this dipole moment's into and out of the page, so then the light will be then polarized into and out of the page, and it will propagate at these, so this would be 90 degrees, this would be 90 degrees, and then this would be also 90 degrees. So it's kind of hard to see here, but this vector is in and out of page, just like we saw for the electromagnetic wave, and that's going to be the axis of polarization. And then it'll essentially have your right-handed coordinate system where radiation will be emitted this way and this way as well. So that's what happens when you have that the dipole moment is aligned so that it's going to oscillate with that electromagnetic wave coming in, and you're going to get a polarization axis like so. Additionally, if we had a different example, and I'm trying to see where I can draw it here, maybe I'll just add it up here. So we have another wave coming in like so, and again, the oscillation we can say is into and out of the page, and instead of having the molecule aligned into and out of the page as well, we can have it say 90 degrees, where now the axis that this molecule will go back and forth across, it's no longer going to be oscillating as the dipole into and out of the page, but it will essentially be as if you have an entire vertical molecule like so, and it will be going into and out of the page like this. So in this case, you have your molecule aligned with that into and out of the page electromagnetic wave, and it's going to go like so, oscillating. And then in this case, you have it perpendicular, and it's going to go into and out of the page like so. In that case, the dipole moment will be, again, up and down. And then we see our donut here is now essentially 90 degrees flipped to this one. So we can see that the dipole moment is again in that axis of the positive and minus sign here. It's no longer into and out of the page. And then we'll see the radiation coming off like so in the other two directions. And in this case, this light will stay in the sky. It will not make its way down to Earth, because we see that the direction of motion is not downwards, because the dipole moment propagation is vertical here. So again, no radiation is emitted along that dipole moment through the center of this donut. So in this case, we just have light radiated off in the other two dimensions. And in this case, we do see the dipole moment in the axis into and out of the page, and therefore there's going to be radiation downwards, and we will see light from the sky being polarized.